of everyone's time, we're going to go ahead and get started. Just by the way, the session is recorded and everything was going to be shared later on, so there's no worries. With that being said, good evening, everyone, or good morning, wherever you are joining us from. It's nice to see some familiar names who are joining us, I think, for a third or fourth time to one of those workshops. A bit of an introduction before we jump right in. FalkorDB is an open source graph database management system. It's designed to manage connected data and complex relationships. And by representing data as interconnected nodes and edges, the system enables efficient storage and super fast retrieval. Today, we're taking a closer look at cluster scale-out and multi-tenancy. And the workshop is delivered by our CTO, Mr. Roy Littman. He's also the co-founder of FalkorDB. He has a lot of experience in the space, so I'm sure everyone's going to have a really nice time. And there is a Q&A session at the end of this, so please pull together your questions. And if there's something burning that you think we need to address as Roy is delivering this presentation, please drop that note in the comment section and I'm going to pull it up and we're going to stop in order to address that. And without further ado, Roy, over to you. Let's get started.
Thank you, Dan. Just making sure that everybody can hear me well and can see my slides.
Yeah, we see the slides and we see you as well.
Okay, good. So thank you for joining and the opportunity to share some of the work that we're doing at Falkor with you guys. This presentation is gonna focus about some of the key features within FalkorDB, and I think general attributes of graph databases, which I think are important. The presentation is accompanied by a demo, which would, as usually the type of demos that I'm giving is a build-up. So we start simple and then we progress. But let's get started. I'm gonna switch over to full screen and let's kick it off. So the type of application that is going to accompany this presentation and demo is one which I believe most of you are already familiar with. And the idea here is to take some type of an access management system. We see this all over the place. You can think about Google Drive, where you're storing your photos or files, and then there's a level of security on top of your resources, which comes in the form of permissions. Who's allowed to access which file? What type of permission does user X have? And how permissions are generally being managed. The same thing goes for AWS with S3 buckets or any general file system that can be found on your OS. So this is the background. This is the type of applications which we would be modeling using a graph. And once modeled as a graph, usually the most pressing question is, does user X have permissions to some resource? That's the common question that is being asked over and over again. And so how does one go about modeling such a system within a graph database? Keeping in mind, usually, as with those solutions that we've just looked at, how does one model multiple customers or multiple different organizations within the system? So you can think about FalkorDB as an organization who's using S3 or using Google Drive. So this is one organization that needs to be managed with its own resources and with its own users. And then there are other companies such as Apple that also have their own resources and their own users, and you don't want to mix those two together. So keeping this in mind, how do we go about modeling all of this within a graph database? And so this is, I think, a straightforward approach. Within our graph, we would have nodes representing users. Other nodes might be representing files. We can have probably directories or folders, and not showing up here, but we might also have user groups. So users might be associated with a group, and a group might have permissions to a file or to a directory. But all of this information needs to be stored within a graph, and with most graph vendors, usually when you have a graph database, it holds a single graph. And so we need to pack all of this information, all of those different organizations within a single graph, and to make a clear separation between user from organization A and a different user from organization B, the common solutions that we see is to apply a second label for every different node. And so a user entity would be labeled as a user, but if that user belongs to FalkorDB, then there would be a second label associated with it that states which organization owns this user. And the same thing goes for any other type of graph entity, such as a file or a folder. And so we have this additional labels that we need to manage that basically mimics the separation between the different entities within the different organization. So this is unfortunately, this is the common solution these days. And it makes your life a little bit harder. Whenever you're writing a query, you need to be careful, and you need to specify under which organization you're currently querying the graph to avoid accessing data that you should not be seeing. So here, for example, we're asking, give me a set of Apple users that have access to files owned by Apple, and tell me how many are there. And so some of the disadvantages of this approach is that there's no real isolation. If somebody writes a query in a way in which the additional labels are not enforced or are not mentioned, they might glimpse into data that they should not be seeing. It's hard to scale this because we're pushing everything into a single graph. And so if the graph gets too big, then we might be hitting some scaling issues. Obviously, there are security risks involved. And so I don't find this approach too appealing. And unfortunately, with some vendors, you just don't have a choice but to model things as such. One solution that comes to mind is to say, okay, if I have one graph per database, maybe I can manage multiple databases, and I would have one graph per database. This way, I'm getting the clear separation. There's no data leakage, and I don't need the extra labels. So things are represented as they should. The problem with this approach is that it might be costly. We need to pay for every database that we're using. It has a higher maintenance because we're managing multiple databases, as many as there are customers. And it might add additional complexity on the application server. which needs to know how to connect to every single database, giving the current interaction that is pending. And so what we really want is this type of architecture, where basically we have a single database which is able to manage multiple different isolated graphs, what we refer to as multi-tenant. And so this is exactly what FalkorDB does. Within FalkorDB, you can have multiple graphs. Each graph is associated with a unique identifier, the graph name or the graph key. And FalkorDB manages a key space or multiple keys, and you just need to specify which graph you would like to query, and you can access it if you have the right permissions. So this is the approach that we're taking. And so this yields an affordable solution because you're only managing one database. The maintenance is pretty low, and you're getting the isolation level that you want for this type of application. All right, and so just to give you a visual view over the data that we will be working with here. Let me see here. Let me run this query once again. And so we're connected to one of our databases. And here you see I have this select graph drop down. And this particular database manages 629 different graphs. I'm just going to pick one at random. This graph manages 148 nodes, and it has 475 edges. Let me just pick some nodes so we would see some data. Let's do 100. So match and optional match. It seems okay. Okay, let me go full screen with this. And so this is one of the graphs residing on the database. We have 4 different types of nodes. We have a group in orange, users in, let's call it blue, a lighter orange for a folder, and the file. And so we can see that this user that has a user ID and a name and an email has access or has permission to all sorts of different files. It also belongs to some user group, and there are a whole bunch of different files here and users. So you can think about this as maybe a graph representation of the resources users that you're managing on Google Drive or on AWS S3 bucket. Going back to my presentation. Now, recall the question. The question that we want to answer basically is, given a user who's trying to access some file, does the user have permission to access this file? And so the benchmark that we're gonna conduct is to see if I have a single FalkorDB database, specifically this one has 16 cores, and I have my application server right here that has, in what I've set up, this one has 8 cores. How many queries, this permission type of query, can I run within a single second? And so I have this all prepared. So let me switch over to the benchmark, and let's run the single shard or single server benchmark, and it's gonna print out the QPS or query per second. Give it a moment. Okay, so we're running roughly around 25,000, maybe 24,000 queries per second, which is not bad, given just a single instance of the database. This is the current throughput that we're able to achieve. But what if this becomes a bottleneck and we want to scale out? Either we might have more than 700 different graphs that we're managing, or the throughput is just not enough. We're not able to cope with the load. And so what FalkorDB supports is a cluster node where you can manage a cluster of FalkorDB databases, all participating in a single cluster. And then what happens is that you can distribute the different graphs that you have across the cluster. And this is exactly what we're going to do. I'm just going to give you some additional information about what is a FalkorDB cluster. So this might be a view for a user of a cluster. Users are not specifically aware that they're talking to several machines. From their perspective, there's a single endpoint, and they are just issuing queries against this endpoint. Behind the scene, there might be a fleet of servers where the data is spread across those machines. And so how graphs are basically spread across a cluster, as I've mentioned, every graph is associated with a key. And these keys basically form a key space. And the key space is separated into slots. The slots are assigned. Each slot is assigned to a single shard. This is a shard or a node. And so every machine is responsible for a range of slots or a range of keys. Usually the keys are evenly distributed. If not, you can move keys around, or you can move slots around. And this cluster here is containing only 3 nodes, but you can scale out and add additional servers to your cluster. Suppose we add an additional machine, and now the key space is being shared among 4 machines. And so some keys would move in order to rebalance the load across the cluster. So this is the current cluster that we're gonna be testing. We have here 6 different machines. 3 of those are take the role of a master. A master is basically a database, a FalkorDB database, which can handle both read and write operations. All of your write operations need to go through the master, and the master basically replicates the data or the changes to its replicas. And so here there's clear separation of 3 masters, and every master has its own replica. Usually you would want to have a master replica set up when you want high availability. In case something goes wrong and the master goes down, then the replica is being promoted into a master quickly, and you're minimizing your downtime. And so this is your classical cluster architecture. And so now, if we were to repeat the process, having our application server or benchmark issuing those queries, not to just a single database, but to the masters within the cluster. And if we recall, we've managed so far to get up to around 26,000 queries per second. Let's see now where we have 3 times the compute power. So let me just check that I have the right configuration. Yes, I do. So let me run this. Oh, yeah, here we go. So now we're able to achieve roughly around 55, 68, 72,000, 60. Yeah, I would say around 64, maybe 62, depending on the measurement. Yeah, it seems around 60 plus on the studies. So we add 3 times the compute power, and roughly we're getting 3 times boost in throughput, which is great. We like linear scalability, and so at least from my perspective, this is fantastic. But why not utilize the replicas? I mean, we've issued all of the queries to the masters. Why not have the replicas participate in this as well? Maybe one reason why not to is because replicas are not fully in sync with the master, and I should be very careful in the way that I say this. There is a tiny delay for the latest change to propagate from the master to the replica. Usually it's unnoticeable, but in some extreme cases, the replica might be in a tiny bit of a delay behind the master. And so for some for the majority of the use case, this is perfectly fine to be querying the replica, but I think you should be aware of the fact that the replica is usually a tad bit behind of its master, especially in cases where you have a lot of writes coming in. Just keep this in mind.
Roy, I'm sorry to interrupt you. There's a good question here that came out. Is the increase in queries per second linear by adding more nodes?
Adding more machines? Do you mean nodes by saying machines? What does node stands for?
Vladimir, could you refine your question, and we'll take it at the end of the session? Roy, let's continue, and we'll pick it up at the end of the session.
Sure. Okay. So now...
Oh, sorry. He's saying masters or replicas.
So this is what we were showing here. So let me run this third and last benchmark, and hopefully we will still be getting linear scalability. So now, once again, we're doubling. Now we're doubling the compute power, going from 48 to 96. So let me just adjust my benchmarking script here. I need this to be true. And this needs to be true as well. Okay, and now I can rerun my benchmark. And so, yeah, we're getting 120. Yeah, 120. Okay, stopping this. And these are the final results. We started with a standalone machine that had 16 cores, and we were getting about 26,000 queries per second. We have tripled the amount of cores, and then we, depending on the average, we've almost tripled the amount of queries that we managed to process. And then we've doubled the amount of cores, and we got linear scalability in terms of queries per second. I did not take this any further. Basically, AWS told me I can't have more virtual calls on this region, so I've stopped here. But I want to believe that this linear scalability continues on as you grow. This needs to be double checked, but because of the way the cluster is managed, I don't see a hard limit or a point in which, if you're managing a huge cluster with, let's say, hundreds of nodes means a machine in the cluster, then you would not be getting something that is close to a linear scale. Basically, each query identifies the server it needs to execute against. The query is sent to that cluster node, and the query is run. So that's basically what's going on here. And with that, yeah, I believe that we're done, at least in terms of the content that I wanted to present. Feel free to jump in with any questions. Done?
Okay, so we have a few questions that we got pulled here. We're going to start off with the first one. One moment. First one is, can I add more replicas if I want to achieve more operations per second?
Yes. You can add multiple. So this is a good question. Here we saw a one-to-one relation between a master and its replica, but you're not limited to just a single replica for a given master. You can have multiple replicas following the same master. And this is a good point where you want to scale out your read operations. So you can think about this master number 3 having 10 different replicas all following that master. And theoretically, you can scale out by a 10x the amount of read queries that you can run against the graphs stored within this slot range owned by this master.
The next question, Roy, is the multi-graph functionality available in our open source version?
Yes, it is available. There's, at least on that front, there's no distinction between what we have as a managed service or available in the open source. It is extremely easy, and maybe I can demonstrate this real quickly, how you can work with multiple graphs stored on a single FalkorDB open source database. So I can actually use our Docker image. So let me quickly pull and run it. What have I done wrong here? Pulling is up to date. Response from daemon. Hold on one moment. Yeah, I already have a database up, so excuse me. So this is a clean FalkorDB database. If I run keys store to see all of the graphs, or graph.list, maybe I should. I don't have any. But then I can actually run a query that would create a graph this time. Let's call this graph A. So this is my first graph. And I might have a person, and that person might have a name. So this is my first graph. I can do graph list, and I can see A. But then I can just repeat the process and say, let's do Z. This is the identifier or the key for this graph. And this time I want to say, maybe I have a flight, and flight number might be A7822. And that's it. Now, if I do graph list, I have my two graphs, and I can query one of them by saying graph.query A, give me all of the nodes in this graph. So we match and return. And yeah, here we go. And if I switch from A to Z, here's my flight. So I can have as many graphs as I want, as long as there's enough RAM in my system to accommodate all of them. And if I run out of RAM, I can fire up a cluster and distribute the graph between the different machines in my cluster.
There's a follow-up here. Is there full isolation between the masters and the replicas? And the clarification that was given here, meaning if I run a query, is it affecting communication with other masters and replicas?
No. So yes, there is a full isolation between the master and the replica. Usually those are different machines. You can actually run a FalkorDB cluster all within a single machine. So every instance or every process of FalkorDB runs on the same machine, but usually, that's not what you're doing. You have different machines running the cluster, like the one that I've set up here. I have 6 different machines. Each one of them is running a FalkorDB instance, and they form a cluster. But in terms of isolation, when you run a query on a master, for example, if that's a read query, it doesn't affect anyone within the cluster. It is run locally on this master, for example, and that's it. Nobody is aware of it. Unlike a write query that changes something within your graph. A change might be in the addition or removal of a node, the introduction of a new edge, or the removal of an edge, maybe in an attribute update. And that write query must run on the master. Once the change is computed, then the master is using its replication link to send the changes over to the replica or replicas if you have multiple replicas following a single master. So the interaction between a master and its replicas happens usually when the master had processed a write query that made a change to the graph, and that change needs to be replicated in order to keep the replicas in sync.
The next one, Roy, is a little bit slightly longer, but it's really interesting. So, are multi-tenant graphs a good mechanism for sharding? For example, is it possible to efficiently overlay multiple graphs in a similar way to how GraphBlast handles adjacency resolution? And there's a use case here. Use case would be outlier detection across multiple data sets that as a whole wouldn't fit in a single host.
I think I lost you midway. I followed the question up until the point where you said something about graph plus and adjacency matrix. If you can repeat that.
Sure. Are multi-tenant graphs a good mechanism for sharding? Let's start with that.
So no, I don't think so. In my mind, sharding is the process of splitting the key space among multiple machines. So with a single machine, the entire key space belongs to that single database instance. When you add additional servers, the operation of splitting the key space among those different servers is called sharding. At least this is the terminology that I'm familiar with. So when you're saying sharding, in my mind, it is the process of moving some of the data from a set of machines to usually a larger set of machines. This is sharding, at least from my perspective. So no, multi-tenancy on a single machine, I would not. I mean, this is not sharding, at least in my mind. This is just managing multiple graphs in a single database.
There's just in the interest of time, Sam, we did get your question. We're going to circle back with Roy after the session. We're going to shoot you an answer. The next question we have is, what happens if a write is acknowledged by the master, but the replica fails before applying the change?
Okay, yeah, this is a good question. So, I mean, in terms of replica failure, I'm gonna assume that the replica went down for, I don't know, for some reason. Let me move to a slide that I can work here with. So this master 3 had processed a write query. It made some changes internally. For example, a new node was added, and then it wishes to replicate that change to the replica. But this one and only replica went down for some reason. Then the change was not replicated, but you're still able to work with this master. When the replica rejoins the cluster, when it reconnects with its master, there's the process of resyncing the replica. And there are two options when it comes to bringing the replica up to speed. If the amount of changes that was accumulated during the time the replica was down is relatively small, then the master would send a delta. It would just remember the set of changes that it wanted to send over but couldn't, and it would send them, replicate them to the replica. If that's not possible because the replica was down for a longer period of time, and this internal buffer that remembers a small delta exceeded its limit, then we don't have a choice but to perform what is known as a full synchronization. Basically, the master would take a snapshot of its entire data set, and it would send over this data set to the replica. This is called full synchronization. It is slower, but we don't have a choice. We need to bring the replica up to speed, and it needs to get all of the data.
Another question we got was, is there an option to run a master query distributed between multiple graphs, meaning within the same master or multiple masters, and returned as one result, not two separate results?
No. Yeah, that's a good question, and it's a request that I am encountering from time to time. Within FalkorDB, when you're running a query, you're running it against a single graph. You cannot run this query against multiple graphs at the same time. So for example, you cannot do query A, comma Z and say, I want to find some node N from, I don't know, what would be the sign, from Z and also give me some nodes from A and return both. Let's call this one M. Return all of the N nodes from Z and all of the M nodes from A. No, you can't mix. It's a query targets a single graph.
Excellent. We're going to take one final question. And the question is there any overhead while adding more graphs?
Adding more graphs would obviously consume more memory. Because you're adding more data, it would cause the snapshotting process to take longer because you have more data. But in terms of the query, a single query, as we just said, a single query targets a single graph. Then no, I mean, in terms of latency, latency would not be impacted just because you have hundreds of graphs instead of just a single one.
Excellent. Roy, thanks for taking all those questions, and thanks to everyone for jumping on board. We really hope that you found this workshop beneficial. We try to make it as practical as possible and bring you some insights that we encounter when we are prospecting or from the field. The recording, like the previous times, will be made available probably within the next 24 hours. You can come back and revisit it. And we're going to compile all of the answers that were given here to all the questions. And we're going to distribute it over email. It's also going to be on our Discord and our blog. So that's also something you can revisit. And of course, feel free to hit us up if you have any other questions on Discord. More than happy to take those. We're having a session like this on the hottest topics, I would say, at least once a month. So please subscribe on the Luma page that we have so that you get invited when we first launch these types of events. And we look forward to seeing more familiar faces next time. And with that, Roy, say we had another great workshop. Thanks everyone for your time.
Thank you.
Bye, guys.